Is everyone ready? Let's get ready for chemistry! Comer, I want to learn important things about the ideal gas equation. That's why I have come here to learn about the ideal gas equation. Well, student coming to learn about the ideal gas equation is pressure times volume equals number of moles times the gas constant R times temperature. So pressure times volume times number of moles times our gas constant times temperature. Now it's important to note several things. First of all, pressure can be in any units of pressure. For example, atmospheres, torrs, millimeters of mercury, kilopascals, bar, psi, can be all kinds of stuff. Volume can be units of volume, usually some sort of length cubed, but more often milliliters or liters. Number of moles can either be moles, or it could be grams, or possibly atoms, I suppose, but I don't think I've ever seen that. The gas constant is always the same thing. We'll talk about that in a second. Temperature can only be in Kelvin. So when you're doing an ideal gas equation problem, your temperature has to be in Kelvin. How do you do that? You take whatever temperature it is in degrees Celsius and you add 273, and that will give you the temperature in Kelvin. So if your temperature is 26 degrees Celsius, you add 273 and you get 299 Kelvin. Or if your temperature is 103 degrees Celsius, you add 273 and then you get 376 Kelvin. So you take whatever temperature it is in degrees Celsius and you convert it into Kelvin. And if you're given a temperature that's not Celsius, well, you're on your own. Find a way to convert it to Celsius and then convert it to Kelvin because it's important. Now the gas constant R is always 0.0821 liter atmospheres per mole Kelvin. So it's always this. Now there are other gas constants out there, but they have other units. The one we want to solve these problems is the one with liter atmospheres. We don't want joules. So this will always be R, and we will always know what R is, because R is always this. Now this just becomes an algebra problem. Here, let's look at an example. A plastic water bottle at 31 degrees Celsius has a volume of 500 milliliters. If the pressure is 775 torr, how many moles of gases are in the water bottle? So when you're given a word problem, the first thing to do is to read it and then get rid of the words. So we don't care about any of this stuff, and we see that the temperature is 31 degrees Celsius. We should immediately convert this into Kelvin. As soon as you find your temperature, you should immediately convert it into Kelvin. Has a volume of 500 mils. Now it told me that that was my volume, but I didn't need it to because milliliters is a unit for volume. If the pressure is 775 torr, so that's my pressure, it pays to become familiar with your pressure units. Question mark word right here, so question mark. How many moles of gases? Moles of gases are in my water bottle. So I have one of each variable. That means this is an ideal gas law problem. PV equals nRT. I have a T. I have a V. I have a P. I'm looking for N, but I don't have R. Except that I do have R, because R is always 0.0821 liter atmospheres per mole Kelvin. So I always know what R is. So let's algebra. We're going to divide both sides by what we know to solve for what we don't know. So we'll divide both sides by R and T. N equals PV over RT. So now we plug in what we have. N equals P, 775 torr, V, 500 mils, T, 304 Kelvin. Now at this point you've got an option. I like to multiply by R, or you could just do the math and divide by R. But I like to multiply up by R's reciprocal here because it makes the units come out cleaner. I'll show you what I mean. Remember that when you divide by a fraction, it's the same thing as multiplying by a reciprocal. So if I have R on the bottom, that's the same thing as 0.0821 liter atmospheres per mole Kelvin. It's just R upside down because I've multiplied by the reciprocal. Now I have Kelvin on top and Kelvin on bottom. Oh boy, nothing else cancels. But I know that for every 1,000 milliliters, there's 1 liter. So I'll want to put 1 liter on the bottom and 1,000 milliliters on, 1 liter on top so that they'll cancel, and then milliliters on the bottom so that they cancel. And torr doesn't cancel with atmospheres. But I know that there's 760 torr for every 1 atmosphere. And you can find that in the textbook. They're usually in the back. So we'll set this up. 760 torr, 1 atmosphere. And then the torrs cancel with torrs, and atmospheres cancel with atmospheres, and everything cancels except for moles, and moles is on top, which is what I wanted because moles is the unit for number of moles of gases. So I feel good about myself because my units work out. It's very important to analyze your units in an ideal gas law problem. It's actually very important to analyze your units all the time, always, but doubly true of an ideal gas problem. 775 times 500 divided by 304 divided by 0.0821 divided by 1,000 divided by 760 is 0.0204 moles. So that's my answer. That's how many moles there are in this word problem. Oh, I didn't finish canceling out stuff. We don't need the water bottle. We don't need that. How many moles of gases? How many moles of gases? 0.0204. Let's do another word problem containing obligatory words. When I look at a word problem, I don't see the words. Sometimes you need to read the word problem for comprehension, especially if there's hidden information. But it's a good idea to just start making a list anyway. So nobody cares about all of that stuff. But I see that I've got 0.5 grams of carbon dioxide. That's probably going to be a number of moles, because I can take this mass of carbon dioxide and turn it into moles using the molecular weight. So that's something. Blah, 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 blah. 3 liters. Okay. Blah, blah, blah. Oh, there's my question word. What temperature? So question mark temperature. Blah, 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 blah. 206 kilopascals. 206 kilopascals. So that's my pressure, because kilopascals is my pressure. And then I am going to start with the equation. PV equals nRT. Do I have a pressure? Yep. Do I have a volume? Yep. Do I have a number of moles? Probably. Do I have an R? Yes, I do. I always have R. It's always 0.0821 liter atmospheres per mole Kelvin. Yay. So I always have R, and I'm looking for T. I have one equation and one unknown, which means I can algebra. So let's algebra. We're solving for T. We're solving for T, so let's move N and R to the other side. Bing. So T equals PV over NR. This time, for funsies, let's just keep R on the bottom, and I'll show you how the units work out when you don't multiply by R's reciprocal. So T equals P, which is 206 kilopascals, V, which is 3 liters, N, which is 0.5 grams of carbon dioxide, and then R, which is 0.0821 liter atmospheres per mole Kelvin. Now we do moles to cancel with grams, except that we're working down here, I guess. So the molar mass is 44.01 grams of CO2 for every 1 mole of CO2. So mole cancels with moles, and grams cancels with grams. And okay, and then kelvins are unit that we want, and kilopascals have to cancel with atmospheres. So I guess we're working with this fraction line here. So we have 101.325 kilopascals for every 1 atmosphere. So atmospheres cancel with atmospheres, and kilopascals cancel with kilopascals. Oh, and liters cancel with liters. Yay! Leaving us with Kelvin, and boy, I sure hope that that's where it needs to be. And it is, because Kelvin is on the bottom of the bottom. And when you have Kelvin on the bottom of the bottom, that's the same thing as multiplying by the inverse, so Kelvin is actually on top when it's on the bottom of the bottom. So, yeah. So bottom of the bottom is actually on top. And we'll use extra smiley faces because people are intimidated by fractions. So temperature equals 206 times 3 divided by 0.5 divided by 0.0821, and then 44.01 is on the bottom of the bottom, which puts it on top, so we'll multiply by 44.01, and then we'll divide by 101.325 because it's on the top of the bottom, which is the bottom. So the temperature comes out to be 6,539 Kelvin, paying absolutely no attention to sig figs whatsoever. Yay. 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 Having trouble. Okay, smiley faces. Smiley faces don't require spelling. 6,539 Kelvin is my answer. Let's do another problem. A giant elastic cat balloon, probably a balloon, at 16 degrees Celsius and 1.16 atmospheres contains 80.3 grams of helium. What must the volume of the almost certainly a balloon cat be? So we have a temperature which is 16 degrees Celsius. I know that because degrees Celsius is a temperature unit. And then this one is unit for pressure. So my pressure equals 1.16 atmospheres. And then, I got an 80.3 grams. This can be used as your number of moles, provided you know what the molecule is. If you don't know what the molecule is, you can't find the molar mass. And if you can't find the molar mass, then you can't turn grams into moles. But since we know that it's helium, that's not a problem. So 80.3 grams of helium. Question word, volume. So volume equals question mark, and then of course we always know R, which is 0.0821 liter atmospheres per mole Kelvin. So PV equals nRT, and then V is question mark. And we need to solve for V by dividing both sides by P. V equals nRT over P. V equals in 80.3 grams of helium. T, I should have converted that into Kelvin. So 16 plus 273 is 289 Kelvin. And then P is on the bottom, 1.16 atmospheres. And then I'm just going to keep multiplying. I'm just going to pull R out and multiply by it as a fraction. It's on top, so it's right side up this time. And I liked that better than having a bottom of the bottom and a top of the bottom and a bottom of the top. And I'd just rather do this. I like having one fraction bar that goes the whole way. So grams of helium don't cancel with moles of helium, but I hope by now that that's kind of trivial. 4.01 grams of helium, 1 mole of helium. Grams cancel and moles cancel. Our volume is 410 liters. Again, paying absolutely no attention to sig figs whatsoever. Just how do you solve an ideal gas law problem? You do algebra, and then you plug in everything and cancel the units, and then you write down your answer, possibly with a superscript smiley face. Obligatory words for our word problem taking up space, but all we really need is 77.7 liters, and that's a volume, because liters is volume, blah, 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 blah. 305 degrees Celsius must be my temperature, because degrees Celsius is a temperature. And you're not going to get me this time. I'm going to convert to Kelvin right away, because boy, if you don't, you're going to be in trouble. So converting to Kelvin, and then grammar, 2.98 moles. Hey, how about that? They just gave us the number of moles. And by they, I mean me, because I made this problem up, if you can't tell. Blah, 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 grammar, asking about the pressure. Okay, so pressure equals question mark. So the thing to do is to take the word problem and then to get rid of the words. And then, of course, R is 0.0821 liter atmospheres per mole Kelvin. PV equals nRT. We have a volume. We're looking for pressure. We have a number of moles. We have an R, and we have our temperature. So we have everything we need. We'll just divide both sides by the volume. So P equals nRT over V. P equals 2.98 moles, 578 Kelvin, 77.7 liters. R is right side up. Ta-da. And the answer is 1.82, definitely not significant figures, atmospheres. Actually, I think the significant figures for this particular one is right. How about that? And then a little smiley face, just so that we feel better. Yay! Smiley face! By the way, it's not a good idea to make up word problems when you're bored and tired and it's late at night. So yeah, 1.82 atmospheres. Is everyone ready? Let's get ready for chemistry! Yeah, 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 yeah.